Hey everybody, welcome to our first online lecture number 16 for MEE 473 RCL 573 with Dr. Rydge Mulford. Okay, we're going to try this format. We'll see how this goes. Feel free to give me some input. Alright, so today we are going to be discussing hydropower. Like I showed before, this is lecture number 16. Okay, so this first video is going to be all about the resource. Okay, so we have the Earth, and we have the sun, and the sun is shining onto the Earth, and the Earth is emitting heat into deep space. All right? And so what we have is we have the sun, which has a temperature of 5,800 Kelvin, okay, which means it has a very high temperature, obviously. So this energy comes to the Earth, right? And then it leaves the Earth. And it's emitted into space, which has a temperature of 4 Kelvin, which is a very low temperature. So you see that solar energy flows from hot to cold. The flow of energy is this direction. Okay, so that's solar energy. We also see the same thing for wind energy. Here's the Earth again, and now here's the sun. And the sun is shining down onto the Earth, and this is heating the air in this kind of local region, generating an area of high pressure. Then this air flows as wind to a colder part of the Earth, where the Earth is now emitting heat again into deep space, which is really cold. And because it's emitting heat, the air is cooling and dropping, and we have this low pressure area. So we have a high pressure area and a low pressure area. High pressure, low pressure. And we see that wind energy, so the energy in the wind, actually flows from a high pressure to a low pressure. Okay, so just like solar energy, we have wind energy, which is also flowing from high to low. And again, that flow of energy is from high to low. Okay, so now let's talk about hydropower. So we've got these mountains, and then we've got this slow, steady drop until we get to the ocean. Okay. So, on the mountains, we've got these clouds, and those clouds are raining water down onto these mountains. And then that water coalesces into one body, a stream or a river, which then flows all the way to the ocean. And so we see that we have water flowing from a high elevation to a low elevation. And so just like with solar power and just like with wind power, we have water which now flows literally from high to low. Okay, before with solar we saw that our high was a temperature and our low was a temperature. And then with wind, our high was a pressure and our low was a pressure. Now with water, our high is an elevation, an actual measurement, a height, a distance above some low elevation. So energy flows along with this water and is flowing, if you will, downhill, literally, from high to low. Okay, we have the water cycle then to thank for this. For solar energy, we had the sun. For wind energy, we also had the sun. And now for hydropower, we also have the sun to thank for the fact that we can extract energy from the water. So let's talk about the water cycle for a minute. Okay, so we've got our mountains again. And we have this decrease in elevation, and then we have the ocean. Okay. So now we're going to draw what the water does. So here's a bunch of water in the ocean. And we'll start off as these clouds over the mountains. And these clouds are going to rain moisture down. Oh, whoops, I'm not sure how that happened. Down into the mountains, and then those mountains, all the water coalesces and falls in this stream and goes into the ocean. But then once we get to the ocean, what's going to happen, right? It kind of is a closed loop. You start high, you go low, like a marble falling down a marble track. You get to the bottom, you're done. Well, that's where we need energy input into the system, and that's where the sun comes in. So the sun uses its energy to heat up the water, and the water then evaporates, both from this stream and from the ocean. And as it evaporates, it forms new clouds. And these are some high pressure clouds, and these are some low pressure clouds. And so, like we saw with wind, we have a flow of water, not just energy, but of actual mass from high to low. And we now have this cycle going on around and around. And so really what matters here is that for hydropower, all it really is stored solar energy. Right? Where did the energy come from? Like we saw, if we started here and then flowed downwards, we get to the bottom, we're stuck. But the sun introduces energy, raising that water up against gravity, and then we have the ability to once again do work. So really, hydropower is just stored solar energy. So that's the water cycle. Let's talk about how that energy actually manifests itself. Okay, so we're going to talk about potential energy. Okay, so potential energy is just work that is being done by gravity. So let's say I have a person, and then turns out they're above the ground. So that person is not just in trouble. Well, they are in trouble because they are some distance above the ground, which is why they're frowning. Some distance h, and they have some given amount of stored energy because they have the ability now to do work because of gravity. All right, so the amount of work they could do, or the amount of energy they currently possess some height above the ground, is equal to their mass in kilograms multiplied by some gravitational constant, the acceleration due to gravity in meters per second squared, multiplied by h, where h is our height above some, what we will call sink. Here the ground is the sink. We call it a sink because you can't go any lower than that. You're going to hit it and you're done. And so generally sea level is what we consider to be a sink. You can't really go any lower than that. That's about as low as you can get. Sure, you could go lower, but in theory, if the sea could reach all of these different kind of places below sea level, it would fill that in, and then everything would still be at sea level. Okay, so this is our potential energy. This equation tells us the amount of energy we have, or the amount of work we could do because we are raised some distance above the ground. Okay, so as we saw, potential energy depends on height. Now, you can have, oh dear, you can have two things with different amounts of potential energy then. Let's say we have two rocks that are two different distances above the ground, one H1, one H2. And they have some difference between them of delta H. Well, I could write the potential energy of rock number 1, which would be the mass of the rock times the gravitational constant times the height of rock 1. I could also write the potential energy of rock number 2. That's going to drive me nuts. Which is the, oops, sorry buddy, which is the mass of the rock times the gravitational constant times height number 2, which means we could find the change in potential energy. So the change in potential energy is equal to the mass times the gravitational constant times delta H. So that's the change in potential energy from this point to this point. Now, if we had suspended this rock at some point and then let it go and allowed it to fall, that potential energy would have transformed into kinetic as our rock accelerated from the top and then picked up speed until it reached this point. The amount of speed it gained between here and here we could have found by calculating the difference in potential energy between those 2 points. All right. Likewise, as water decreases in height, so as we see water decreasing in height, then the potential energy of that water, transforms. Okay, so let's say we've got some river and it's flowing along, and then it comes to a part where the river goes down. Okay, and so I think what we would expect to see, right, is we have this water and right here it's flowing normally. Then you would expect during this part the water to accelerate, right, as this potential energy is transformed into kinetic energy. In theory, we'll be going faster here, but we have friction along this ground, and that extra kinetic energy it picked up eventually turns into heat. So the difference in the height of the water here, the delta H of the water being the difference in its potential energy, we call head in this industry. So the head of the water, how much height you have. So head is drop in elevation. Okay, and to give you an idea of what I'm talking about. All right, so see here, here's the height of our water. We see a very small decrease and then the new height of our water. The difference between these two heights would be the head of our stream. Now you see here we have nice easy flowing water, and here we have turbulent water. The potential energy that this water had, it had potential energy, that was transformed into kinetic energy as it fell, and then finally into thermal energy once that kinetic energy experienced friction. And so that kinetic energy was very turbulent, it tossed and it turned, and then that eventually just turned into heat. That is because of the second law of thermodynamics. Okay. So now let's talk about what kind of potential we have in this country. So here you see the United States, and we have, in red is small hydro plants, so some that don't put out very much. And then the yellow squares are existing, generally large-scale hydropower plants. And you see those are concentrated where you have elevation. So you get a lot over here on the west end of the Rocky Mountains, and then throughout the Rocky Mountains. You also have quite a bit up here where there's a lot of water, and here where there are some mountains and a lot of water. So there's two things that you need. You need elevation, and you need water. So like Nevada, nothing. There's actually a lot of elevation, but there's no water. West Texas, nothing. Most probably for both reasons, honestly. And then here in Ohio, you see, although we have a lot of water, we don't have a lot of head or a large drop in elevation all of a sudden. So that doesn't do a lot for us. Here we have by state the amount of feasible, so possible drop in head that we could utilize. Other availables, there is head, but it's used for something else. Excluded is usually because of it's a national park or it's a protected nature area, and then developed is we actually have put a dam on that head. And so you see Washington takes the cake, and they also have produced the most hydropower. They get a lot of their power from hydro, but they still have quite a bit of potential. If you look really at most of these states, in fact, they are all the Mountain West and the Pacific West, where you have a lot of water and a lot of elevation. Of course, the king of them all is Alaska. The big problem is almost all of it's locked away for other things. Okay, so that kind of sums up our resource talk about hydropower. In our next lecture, we're going to talk about how we capture this potential energy and turn it into electrical energy.